In this video, I'm going to talk about AI-based methods for reducing the appearance of cast shadow artifacts in wrist x-rays. Before I start, I want to give a big shout out to my dear colleagues, Daniel, Sergio, and Mohammed. Now let's go on a patient journey and say someone is riding their bike, trying to do cool tricks to impress their friends. And then, foosh, they fall onto their wrist. Once the adrenaline wears off, they will likely present to the emergency department with pain, swelling, and a decreased range of motion in the injured wrist. So then this person will be examined by the clinical team for deformity and tenderness, and X-ray imaging is used to determine the presence, type, and location of a fracture. Based on the imaging, the radiologist diagnoses the fracture and the treatment is determined. For this example, the patient had fallen off their bike and the imaging was requested to diagnose a potential fracture of the distal radius. And in this case, the radiologists were able to find the fracture. As you can see here, this one is quite obvious. After the diagnosis is confirmed, the patient is treated by reducing the fracture. During the reduction process, the doctor gently realigns the broken bone fragments using traction and manipulation, in some cases checking the alignment with fluoroscopic imaging. In more complicated cases, open reduction surgery and fixation devices may be needed. After alignment, a cast is molded and applied to immobilize the wrist, ensuring the fracture heals correctly. So, the patient has had their fracture reduced and a cast applied to immobilize their wrist. And about 3 to 4 weeks later, follow-up imaging is performed to check on the patient's healing. Here, the radiology report noted that views through the plaster obscure fine bony detail. And this is something which is typically noted in these radiology reports. So, there is a clinical problem of cast shadow artifacts in wrist x-rays. You can see in this example, in these images, that the fracture is a little bit less obvious through the cast, which is causing a degradation in image quality. It's hard to distinguish whether intensity changes are due to underlying anatomy or just because of the cast. Our solution was based on CycleGAN, which is a type of generative adversarial network designed for image-to-image translation tasks without needing paired training data. It works by learning two mappings, one for converting images from domain A to domain B, and another for the reverse. You can see that this problem was initially conceived to map images of horses to zebras, but could be more broadly applied to image processing problems, such as that of cast suppression. So with our example case, we have furnished some motivation for the clinical problem, which is that fractures are stabilized with casts, but during follow-up imaging, these casts cannot be removed and often obscure the underlying bone. Our initial solution to this problem was to apply what is known as a CycleGAN model to digitally suppress cast shadow artifacts in wrist x-rays. And in our previous study, one of our key findings was that this model enhanced the diagnostic confidence of radiologists reporting on AI-generated images. But another interesting finding is what pushed us to build on this work. The finding came out of a secondary experiment we did with the radiologists, where we fed them 60 images. Half of those were real and half were fake. Half had casts and half did not, providing a balanced data set. So we asked them to classify the images as either real or fake. Then we analyzed the results to see if radiologists were fooled by our CycleGAN model. We found that 36% of AI-generated castless images were classified by radiologists as unenhanced. This shows that typically, radiologists could see that the cast suppression model had been applied to However, 85% of generated cast images were classified by radiologists as unenhanced. So through this experiment, we showed that our CycleGAN model is able to digitally add casts onto radiographs that radiologists think are real. So clearly, it's easier to generate casts than it is to remove them. And this is really what motivated us to take a different approach. In finding that the CycleGAN model is able to generate highly realistic casts onto wrist x-rays, we realized that we could reframe the cast problem into a paired one. Essentially, we selected 10,000 wrist x-rays without casts and applied our CycleGAN model for cast generation, thus creating a synthetic paired dataset of cast and no cast images. So now, when we train a model with this paired dataset, we have a ground truth target image. So assuming the synthetic dataset is diverse and realistic enough, we should be able to train a model that learns how to remove real casts effectively. Thanks to the reframing of the problem into a paired one, we can now train what is known as a pix-to-pix model. You can see some examples here where this sort of model can be applied, converting from labels to realistic videos, from aerial images to maps, day to night, and so on. Thanks to the CycleGAN model trained on unpaired data, we are able to train a model on paired data. So we split our data with an 80-20 ratio such that there were 8,000 pairs for training and 2,000 pairs for testing. So we've allowed ourselves to train a pix-to-pix model thanks to our synthetic paired data, but how do we benefit from this? One of the fundamental limitations of unpaired methods is how do you even objectively measure how good it is at removing casts? We don't know exactly what the decasted image should look like. The first study that looked at cast suppression used the metrics you see described here. These include histogram correlation and intersection, chi-squared distance, and Hellinger distance. Now, since these metrics are based on the comparison of histograms, they inherently suffer from a major limitation. With the example shown here, we can demonstrate the key limitation of using histogram-based metrics for performance measurement. A circle and square of equal area and brightness would yield equivalent histograms despite representing completely distinct objects. This is essentially the problem, and what we found in our study is that none of the models we developed were significantly different from each other according to these metrics. So we quickly realized their limitations, and this is why the radiologist assessments were so important for clinical testing of our model. But the reframing of the cast problem into a paired one is what allows us to escape using these metrics, which aren't particularly meaningful. So we train the pix-to-pix model on our data set for units 256, 512, and 1024. Now that we have a ground truth, we can use more meaningful metrics that make pixel-wise comparisons, like mean squared error and structural similarity index measure. These preserve spatial information. Interpreting the results, we know that a lower mean squared error and higher PSNR and SSIM reflect better performance. Statistical tests show that the UNET 1024 model outperformed all others at removing synthetic casts in all metrics, generating high quality images that match the ground truth target more closely. So in the paired problem, we can now make a properly justified choice of model architecture, which is great, but ultimately, our model needs to be tested on real casts. One example is shown here with an image from a publicly available pediatric wrist trauma dataset. At the far left, we have our original cast image with the zoomed in square showing a fracture. To its right, you first have the CycleGAN cast suppressed image, and then our pix-to-pix models in increasing order of architecture size. It's quite nice to see a visual example like this, as it demonstrates the image texture differences between models. Now, where do we go from here? Moving forward with this work, we investigated how these image processing methods impact automated fracture detection. We compared models trained with and without cast images and tested whether cast suppression pre-processing could improve detection accuracy. What we found is that suppression helped only when models had never been exposed to cast images, while models trained with real cast data consistently achieved the highest accuracy. This experiment reinforced the importance of considering the composition of training data when developing AI models. In terms of future work, a possible next step would be to use CT data of wrists with casts. We could segment the cast and then mask it to 0, creating a paired dataset of with cast and without cast CT volumes. These paired CT volumes could be converted into voxelized phantoms, which could then serve as inputs to Monte Carlo simulations. And from these simulations, we could generate paired X-ray projections with and without cast, providing a novel dataset for developing and evaluating AI-based cast suppression methods. Alternatively, we could think of using dual energy X-ray systems or anthropomorphic phantoms to test such cast suppression methods. Despite many limitations, this study lays the groundwork for developing a pipeline of AI models for the radiology clinic. These AI-based image processing methods have the potential for improving image quality and readability of wrist X-rays that are affected by cast artifacts. Thank you for listening. If you have any questions or comments, please get in touch.